Current class number 3. In this class I will going to discuss alternating EMF applied to pure resistor. In this topic we will discuss expression for current, variation of voltage and current with time, and phasor diagram. And in the next topic, alternating EMF applied to pure capacitor, we are going to discuss expression for current, variation of voltage and current with time, phasor diagram, capacitive reactance and its variation with frequency, and finally related questions to the topics. Hello, good morning students. In previous class we have discussed alternating current and its different aspects. In alternating current we have to know the value of RMS current, average current and average current for half cycle as well as full cycle. And we have discussed what is RMS value of current, what is average value of AC, what is average value of AC for full cycle. Now in this class we are going to discuss how resistor, capacitor and inductor behave with alternating current. In previous chapters, just we can say electrostatics, current, electricity, magnetic effect of current. In all these chapters, we have discussed direct current and how direct current behave with resistor, or how resistor behave with direct current. We know very well, and that is known as V equals to IR, that is Ohm's law. But in this class, I am going to discuss how resistor, capacitor and inductor behave in AC, or we can say whenever alternating EMF is applied to the combination of R or L or C or single resistor or combination of resistor or inductor, then what will be the effective opposition offered to the current, that we are going to discuss. So first topic I am taking alternating EMF applied to pure resistor. Alternating EMF applied to pure resistor. It means here we are going to discuss how resistor behave in AC, and what is here pure resistor. Pure resistor means it is having only resistive effect, there is no any inductive effect, it is pure resistor. So let us suppose this is a resistor of resistance R, and here we have applied an alternating EMF. This is the symbol of alternating EMF. So R is the resistance, and this resistance R is connected to a source of alternating EMF, which is given by V equals to V naught. This is the alternating EMF applied to the pure. V equals to V naught sin omega t, where V is known as instantaneous value of alternating EMF, V naught peak value of EMF, omega angular frequency. Now I think you are understanding it. Now we have to find out current for this resistor, and we know that resistor directly obeys Ohm's law. Therefore, by using Ohm's law, we can write I equals to V by R. Very simple, and therefore it becomes V naught by R and sin omega. And now this V naught by R we can say peak value of current, and therefore it becomes I naught sin omega t. That is equation number 2. Now we have to clearly observe these two equations. This is alternating EMF, this is alternating current. If we see this phase, then here it is sin omega t, and here it is also sin omega t. It means in the case of a pure resistor, voltage and current are in same phase. Voltage and current are in same phase. In the case of resistor, voltage and current are in same phase. It means if we consider phase difference as phi, if we consider phase difference as phi, then here since there is no phase difference, therefore phase difference can be written as 0, or we can say in the case of resistor, voltage and current are in same phase, both vary according to sine function. Here it is also sine function, here it is sine omega t, this is sine omega t. Therefore in the case of a pure resistor, voltage and current are in same phase, therefore phase difference is 0. Now this phase difference or this variation of voltage and current we can also represent by a sinusoidal graph. We can present the graph of sine omega t for V and also for sine omega t for I. So that graph I am representing here. So here we can easily understand this is resistance R. Here it is alternating source of EMF V equals to V naught sine omega t. This we have written V equals to V naught sine omega t. Here I become I naught sine omega t. V naught is the peak value of voltage while I naught is the peak value of current. And we are easily able to understand that in the case of resistor, voltage and current both are in same phase. It means there is no any phase difference between voltage and current. Now this we can also represent by diagram. I am showing the variation of voltage or current with time. On this axis we are taking time. Here on this axis I am taking voltage. Then since we know that V equals to V naught sine omega t, V equals to V naught sine omega t, therefore the variation will be like this. Variation will be like this. This is the variation of alternating voltage having value V equals to V naught sine omega t. We can easily understand this value will be the peak value of voltage, and here this will be also the peak value of. Here we can say time as t by 4. It means 1 by 4th of the time period. Here time will be t by 2. Here time we can say 3t by 4. This is 3t by 4, and here it can be written as t. So this is the variation of current or voltage with time, or we can say how voltage vary with time, that is represented by this time. Now this graph we have drawn for V equals to V naught sine omega t. Now if we draw the graph for I equals to I naught sine omega t. Now if we draw the graph for I equals to I naught sine omega t, we get the same variation. The variation of current will be exactly same as that of the voltage, but the peak value may differ. That's why I am drawing the diagram, or I am drawing the variation of current like this. Here current is also vary just like voltage, but the peak of current may be different, or peak value of current may be different, but both will have maximum value or minimum value or zero value at the same time. It means variation of current and voltage both is exactly same. So this is what about the resistance with AC. How resistance behave with AC? Then it is clear that in the case of resistor there is no effect whether we are applying AC or we are applying DC. The voltage and current both vary in similar manner. And now this variation of voltage and current we can represent by other quantity, or that is known as phasor. We can also use, or we can also introduce new quantity phasor. So here we can represent one phasor. Let us suppose this vector is representing voltage, or this arrow, or from here to here we are representing voltage. Let us suppose peak value of voltage is this. and omega is the angular velocity of rotation of phasor. Initially the phasor is here, and since omega is angular velocity, after t time the phasor is here. Therefore, this angle can be written as omega t. Since omega is angular velocity, t is the time taken. Therefore, this phasor will be at this position after. Now, this vector of this phasor can be resolved into two components. I think you are understanding. On this side, the component will be V naught cos omega t. On this side, the component will be V naught sin, and that is alternating. So by this phasor, we can also represent the current. Now, similar manner, since voltage is in this side, or voltage is represented by V equals to V naught sin omega t, we have to also represent current also in the same phasor. Therefore, we can consider a new phasor, and let us suppose it is having length I. Then, if we mark the component on y-axis for this I naught, then this component will be I naught sin omega. This component will be I naught sin omega t. Hence, we can represent current and voltage both with the help of phasor. And here from this diagram, it is very clear that current and voltage both are in same phase. Therefore, phase difference between voltage and current in the case of pure resistor is 0. Now I think this is very clear. Phase difference between voltage and current in the case of resistor is 0. It means both vary just similar manner because both are having the same mathematical function V equals to V naught sin omega t and I equals to I naught sin. Now we are considering next topic, alternating EMF applied to pure capacitor. It means it is having only capacitive effect. Here we are considering only the capacitive effect of the capacitor. The same topic just we have discussed for resistor, we are going to discuss for capacitor. It means we know that here in this case we have to find out first phase difference between voltage and current, and second what will be the effective opposition of the capacitor to the AC. So for this purpose, let us suppose we consider a pure capacitor of capacitance C. Let capacitance of this capacitor is C, and this capacitor is connected to an alternating source of EMF, that is V equals to V naught sin. Alternating EMF V equals to V naught sin. And here we have to find out the expression for current. We have to find out the expression for current. We know that I was to dq by dt. We know that I was to dq by dt. Although in second unit or in current electricity chapter, generally we write current equals to charge upon time. But here charge is variable. Charge on the capacitor is variable. Therefore, I equals to dq by dt. And since for any capacitor d by dt, q can be written as C. For any capacitor, we know the relation q equals to Cv. There is a relation for capacitor q equals to Cv. That is the basic equation of any capacitor. Q equals to Cv. Therefore, here we can write Cv. Now this C is constant, can be taken out. D by dt and V. V means alternating EMF. So this we have to put as V naught sin. And now this V naught can also be taken out. Therefore, C V naught. And we have to write d by dt over sine omega. So now we have to find out the differentiation of sine omega. I think you know very well the differentiation, but again I am discussing. For example, differentiation of sine 4x. I am giving an example. D by dx of sine 4x. D by dx of sine 4x will be 4 cos 4x. Sine x, if there were only sine x, differentiation is cos x. It is sine 4x, therefore differentiation will be 4 cos 4x. That we have already discussed in class 11 very well. Sine 4x will be 4 cos 4x. Similarly, here differentiation of sine omega t will be omega cos omega t. Therefore, we will write C V naught omega and cos omega. Now we can arrange this equation by making some changes. Here it is V naught, and I can write this omega and C, this omega and C, I can write. Just we will be able to understand why we are writing like this. V naught upon 1 by omega C, this quantity I have written here, and this is cos omega t. We are going to compare the phase, but here the function is of sine, here the function is of cos. Therefore, first of all, we have to convert, or we have to change this cos into sine function so that we can compare the phase. And we know that sine 90 plus theta, we know that sine 90 plus theta can be written as cos theta. Therefore, this cos omega t can be written as sine omega t plus 90, that I am writing by pi by. It means V naught by 1 upon omega c sine omega t plus pi. Now we can compare the phase. Just we are going to compare the phase. But if we see this quantity is constant because V naught peak value, that is constant. Omega angular frequency, that is also constant. C capacitance of the capacitor, that is also constant. It means this whole quantity is constant and it can be written as I naught. And the equation becomes I naught sine omega t plus pi. The whole equation becomes sine omega t plus pi. And this is the value of current. This we can mark as equation 1. Again I am recalling this. V equals to V naught sine omega t. I equals to dq by dt. We have to find out current for this. It can be written as d by dt of Cv, and therefore its C can be taken out, and d by dt V naught sine omega t, that we can write C V naught d by dt of sine omega t. Now differentiation of sine omega t will be omega cos omega t. Therefore, C V naught omega cos omega t. And now we have arranged this equation in this manner. V naught divided by 1 upon. Why we are writing here? Because this whole quantity we are writing as current. And we know that current is voltage divided by resistance, or voltage divided by opposition, or voltage divided by hindrance. So this is the opposition. Just we are going to discuss. This quantity will be the effective opposition offered by the capacitor. And you can easily understand this whole quantity we are representing by peak value of current. It means this is V naught upon opposition. And this opposition will definitely have unit ohm. It will definitely have unit ohm. Name we will change according to the capacitor, but definitely this quantity will have unit ohm. It means it will be the effective opposition of the capacitor. But before discussing this, I am going to discuss the concept of phase difference. Here it is omega t. Now we can easily understand. Here you can look at here sine omega t. Here phase is omega t, but here it is omega t plus pi by 2. It means now in this case voltage and current are not in same phase. They are having different phase, and since phase is different, Therefore, there will be some phase difference. And if we see, it is very clear that there is a phase difference of pi. There is a phase difference of pi by 2 between voltage and current for the case of a capacitor. Or we can say current leads the EMF. Since here it is omega t plus pi by 2, it means in the case of capacitor, the current leads the EMF by pi. Or we can also say EMF lag behind the current by pi. So this we will represent by the phasor. Now I think this is clear. I'm writing the equation here. I equals to I naught sine omega t plus equation number, where I naught equals to V naught by 1 upon omega c. I naught equals to V naught by 1 upon omega c, and this we will represent by new quantity x. Here x is known as reactance. Since it is xc, therefore name will be capacitive reactance. Here xc is known as capacitive reactance, and it is given by xc equals to 1 upon omega c. Or that we can also represent as 1 upon 2 pi nu c. Because we know that omega equals to 2 pi nu, where nu is the frequency. This capacitive reactance we can define as effective opposition. Effective opposition. Effective opposition offered by a capacitor. Effective opposition offered by a capacitor is known as capacitive reactance. It is denoted by xc. The value is xc equals to 1 upon omega c, and that we can also write 2 pi nu c, and unit of capacitive reactance will be, it means capacitive reactance will play the role of resistance. Resistance plays the role for resistor, and the capacitive reactance will play the role of opposition for the capacitor. Now we are going to discuss the behavior of capacitor. Behavior of capacitor for different frequencies. That is very important concept. First we are taking for very high frequency. Very high frequency, for very high frequency, it means we can say nu tends to infinity. Also nu is not infinity, but we are saying that the value of frequency is very high, and from this diagram, from this formula, it is very clear that xc is inversely proportional to frequency. xc is inversely proportional to frequency. It means for nu tends to infinity, xc tends to 0. It means effective opposition becomes 0. Hence, we can say that a capacitor behaves like a short circuit. A capacitor behaves like a short circuit at high frequencies. Why short circuit? Because here effective opposition becomes 0, and we know very well that whenever effective resistance or effective opposition becomes 0, we say it becomes short circuit. It means at very high frequency, the capacitor will behave like short circuit. At very high frequency, capacitor will behave like short circuit. At very low frequencies, nu tends to 0. At very low frequency, nu tends to 0, therefore Xc tends to infinity. For very low frequency, nu tends to 0, therefore Xc tends to infinity, and therefore current will be 0, and hence we can say that at very low frequencies, Xc will be infinity. It means the capacitor will behave like open circuit. The capacitor will behave like open circuit because the impedance of the circuit will become so high that it does not allow any current. Therefore, the capacitor will behave like open circuit. So this is the discussion. First, at very high frequency, now at very low frequency. Third, for DC, if we talk about direct current, for DC, the nu is 0. We know that, we have already discussed in previous class. Nu equals to 0 for DC. Direct current frequency will be 0. Therefore, Xc will be exactly infinite, and hence again it behaves like open. It means by knowing the value of Xc, this is a very important parameter for capacitor. By knowing the value of Xc, or by knowing the value of capacitive reactance, we can find the behavior of capacitor for high frequency, for very low frequency, and for direct current. So this is the discussion about capacitive reactance. Again, I am discussing the formula. Xc equals to 1 upon omega c, or we can say 1 upon 2 pi c, and then we can find the value of capacitance, capacitive reactance for different cases. Now we are coming to the point of this phase. Here it is very clear that in the case of capacitor, V equals to V naught sin omega t, I equals to I naught sin omega t plus pi by 2. It means the variation of voltage and current will be different in the case of capacitor. This we can easily represent with the help of phasor. That will be suitable here. Let us suppose this phasor is the phasor for EMF for voltage V naught. Omega is the angular velocity of rotation of phasor, omega. Therefore, after t time, this angle will be, and therefore we can easily understand. I am not drawing the component here. We can easily understand that this component of, or we can say y component of this V naught will be V naught sin omega. So this is the phasor for voltage. This is the phasor for voltage. But here it is written I equals to I naught sin omega t plus pi by 2. It means the current is ahead of EMF by pi by 2. Therefore, this we can introduce in new phasor having value of angle 90 ahead of this voltage. This we can represent by I. So this is the phasor diagram for capacitor between voltage and current. Or we can say this is the phasor for voltage, this is the phasor for current. But from this phasor diagram, it is clear that in the case of capacitor, phase difference between current and voltage is pi by 2. It means current is ahead of EMF by pi. And we can also represent both these two graphs with the help of sine cosine function. From this graph, it is clear that V equals to V naught sin omega t. Therefore, when omega t is 0, this value will be 0. But it will have 0 plus pi by 2. It means it will have some value. It means both these phasors or both these functions varies differently if we draw the. So this is the phasor diagram for voltage and current in the case of a. So this is what about the behavior of capacitor for alternating current. As a summary, we have discussed that in the case of capacitor, the effective opposition offered by the capacitor will be denoted by a new quantity, that is X Xc. Clear? That is Xc. This is known as reactance, and here C for capacitor, therefore this combined is known as capacitive reactance, and the formula is 1 upon, and that will be very, very important for alternating current when we discuss capacitor, inductor, or now we are discussing 2-3 questions related to this. The question first is, what is phase difference? What is phase difference between voltage and current? What is phase difference between voltage and current? What is phase difference between voltage and current? Number 1 for resistor, and number 2 for capacitor. So here we can say in the case of resistor, phi will be equals to 0. In the case of capacitor, phi will be equals to plus phi by 2. It means current is ahead of EMF by pi by 2. Current is ahead of EMF by pi by 2. And in the case of resistor, both are in same. Second question. Capacitive reactance Xc of a capacitor is 1 upon omega c. And let us suppose it is having value 20 ohm. Directly I have given to you that capacitive reactance of a capacitor for a particular AC or particular value of AC is 20 ohm. Question is that what will be Xc? What will be Xc if frequency is double? If frequency is double, number 2, AC replaced by DC. AC is replaced by DC, and third, dielectric slave that we have discussed in electrostatic chapter. Dielectric slave of dielectric constant epsilon r equals to 2. Dielectric slave of dielectric constant epsilon r equals to 2 is introduced between the plates. So these are the 3 questions. First question, second question, third question. I am serially solving A part. So we can say this is A part, this is part B, and this is part C. AC frequency become double since we know that Xc equals to 1 upon omega c. So therefore frequency become double, hence capacitive reactance will become half. Therefore in first case Xc will become Xc dash, we can say new capacitive reactance will be Xc by 2 because frequency become double, and here we know that omega equals to 2 pi nu, therefore it will become 20. In the second case, AC is replaced by DC. So just we have discussed that for DC nu equals to 0, therefore omega will be 0, and hence Xc will be infinite. It means in this case the capacitor will behave like opposite. Third C part, dielectric slave of dielectric constant 2 is placed between the plates of the capacitor. From electrostatic unit, I think you all might be knowing that C dash equals to K into C, or C dash is epsilon R into C, where epsilon R is the dielectric constant. It means whenever dielectric slave is introduced between the plates of capacitor, its capacitance will increase, and here in this case it becomes 2 times. Since capacitance becomes 2 times, therefore again Xc become half. So therefore Xc dash equals to Xc by 2. Why 2? Because in this omega C factor, C become double, therefore Xc by 2, and again the answer will be here Xc by 2, that is 20 by 2, or that we can also write 10 ohm, and here it will be also 10. It means capacitive reactance will become half. In this capacitive reactance also become half, but here why half? Because frequency become double, and in this third part or this C part, capacitance become double, therefore capacitive reactance become double. So this is what about the behavior of capacitor in alternating current, or how capacitor behave with AC. Thank you.